Good evening, children. Today we are going to start with a new chapter, which is your chemical equilibrium. Okay. So before understanding what chemical equilibrium is and the related questions, so first we'll see what equilibrium is. Right. For a general equation, A gives rise to B. Okay. So when A converts into B, that is called as the forward reaction, right? That is the forward reaction. When B is trying to convert into A, that is called as your backward reaction. That is called as the backward reaction. So what happens, what do you mean by equilibrium is that the rate of this forward reaction is equal to the rate of backward reaction. That is called as your equilibrium. I hope you all are knowing all these small concepts. So let us begin with the questions and we'll understand the concepts along the way. So the first question is on your screen. I want you all to pause the screen and try this question, everyone. Okay, children, let us see what is given here. So we are being given with equation 1 and equation 2, right? Here we see that it is given to us AB plus half B2, and all of them are in gaseous state, right? So we know that this is the first equation. Now the second equation is if we ignore the coefficients, okay, if we ignore the coefficients, can I say that the second equation is the reverse of the first equation? Yeah. If we reverse the first equation, we get the second equation, right? Yeah. Also, we see that to the first equation, if we multiply 2, if the first equation is multiplied by 2, then also we get the second equation. So two things have been done. One is you have reversed the equation and you have multiplied it with 2, right? Now, for any equilibrium constant K, what is the formula, children? It is the concentration of product raised to the stoichiometric coefficient divided by the concentration of reactant raised to their stoichiometric coefficient. Yes, but in products and reactants, we take only those things that are in your aqueous state or in your gaseous state. The state that we ignored is your solid state. The state that we ignore is your solid state, right? So when we are taking into consideration, okay, we take only aqueous state or gaseous state, we ignore solid or liquid state. This is not being taken, right? In case of gaseous state, we take pressures as well, right? We take pressures as well, right? In mostly we take pressures. Now if I tell you, when you're multiplying something with the equation, when you multiply something with the equation, that changes into the power, for example, if the equilibrium constant of the first reaction is k1, then it will be concentration of AB2 divided by concentration of AB B2 to the power half, which is the stoichiometric coefficient. If I write K2 here, K2 is going to be concentration of AB, B2, AB2, right? This is what it is going to be. So if I see in both the equations, I can say that this K2 is reverse of K1. The first thing that we get from here, that this K2 is reverse of K1, right? Yes. Second thing that we see, that we have multiplied 2 with this K1. So when you multiply something, if you are multiplying, it becomes power. So this is going to be power, right? So now if I cross multiply this both, it is going to be K1 square into K2 equals to 1. So this, children, is going to be your answer, and this one is present in option number C. So option number C is going to be your answer. From here, what are the takeaway points that we understood? We understood that if forward reaction has an equilibrium constant of K, a backward reaction will have an equilibrium constant of 1 by K. If you're multiplying this with N, then it is going to become K to the power N. Yes, that is how your equilibrium constant changes. Okay, let us move on to the next question. Certain things that you need to know here. The same thing that I told, it is definite value for all value of chemical reaction. That is, we are talking here about your equilibrium constant. If a reaction is written in opposite way, Kc of is inverse of the another case. So we can say that the second K2 is equal to 1 by K1. Okay, that is what we are talking about. A similar kind of question, okay, whatever we learnt in the previous concept, based on that concept, this question is there. I want you all to pause the screen and try. Okay, children, I hope you all would have done it. What is given? The equilibrium constant for the reversible reaction. Okay, so something is given to us here. It's given 2A, 2B plus C. It is given to us as K1, right? Yes. Now, for the second reaction, it is 3 by 2A, 3 by 2B. This is given to us as Q2. Yes. So we can see all of them are in gaseous state, so that's not an issue. Now it is asked to us that how are K1 and K2 related to each other. So how do we know that? We'll see what changes has taken place. Has it been reversed? So no reversion, right? But something has been multiplied, right? And what has been multiplied, children? Directly you can see. How do you see what has been multiplied? You see where 1 is there. Here 1 is there. So this is 3 by 4 times. So 1 into 3 by 4 times. 1 into 3 by 4 times is giving you this. So let's see if it is working for others as well. So this 2, if I say here 2 into 3 by 4 times, I'm definitely going to get 3 by 2. Similarly for this, 2 into 3 by 4, if I do, obviously this is the same as this is also going to be 3 by 2. So we have multiplied this entire thing with 3 by 4. We have multiplied with 3 by 4. Yes. So whenever we multiply, that goes on to the power. Yes. So can I say that K2 is equal to K1, and 3 by 4 has been multiplied, and when you multiply, that goes on to the power. So K1 to the power 3 by 4. And that is in which option, children? Again, in option number C. Right? So this is going to be your correct answer. So we learned a concept and we understood that how things are done. Okay, moving on to the next question. Next question on your screen, children. Try to attempt this easy one, not that difficult, but you'll have to do it carefully, right? Okay. Okay, children. I hope you all would have done that. Now, what is given to us here? It is given that there is a reaction. And what is that? A, right? Okay. The relationship between dissociation constant K and degree of dissociation alpha, right? We want the relationship between dissociation constant K and degree of dissociation alpha, right? So basically we are talking that A is undergoing some decomposition or dissociation into B and C. So obviously when it dissociates, how to the extent to which the dissociation take place, that is called as your alpha, right? This gives you the extent of dissociation. Yes. So what is the relationship that we want to know? So if you want to know the relationship, you have to express the equilibrium constant in terms of alpha. Yes. If you want to express, you have to express the dissociation constant in terms of alpha. So if we talk about K, what is going to be K, children? K is going to be P of B. Yes. Into P of C to the power 1 by 2 divided by P of A. Yes, because this is the general rule of your equilibrium constant, that we have to take partial pressures in case of gases. So what partial pressures in terms of gases? So we have taken in general. Okay. Now what is given? So if this is a general equation, can I say that initially the partial pressure was Pi? Yes, we'll write the equation here again once more. So initially, if I talk about the partial pressure was Pi, here this is nothing has come, so this was 0. Now it dissociated. Suppose I tell you there is 20% dissociation. Initially it was X, there is 20% dissociation. So how much is remaining? How are you going to say, children? You are going to say that this is X, it was originally X minus, now 20% dissociation has taken place, that is 20 by 100 into X. Right? This much is remaining. So this 20% is nothing but alpha. This 20% is nothing but alpha. So 20 by 100, so this is nothing but your alpha. So x minus alpha x, which implies I'll write x into 1 minus alpha. Yes, whenever there is dissociation, we are going to write it in these terms. Yes, okay. So here also some dissociation has taken place and we don't know how much dissociation has taken place. So what are we going to write, children? We are going to write this is going to be pi into 1 minus alpha. So this has dissociated this much. Now here what, as the coefficient is 1 here, so here it will, alpha will be formed here. As the coefficient is 1 by 2 here, so alpha by 2 will be formed here. Yes, alpha by 2 will be formed here. Now, if you add all of this, what are you going to do? If you are going to add all of this, you are going to get the equilibrium pressure, right? If you add, so we want the equilibrium pressure. Yes. So let the equilibrium pressure equals to P, and that will be equal to how much, children? We are going to add all of these. So if we are going to add all of these, what are you going to get? Yeah, so you are going to get pi minus pi into alpha plus pi alpha plus pi alpha by 2, right? So this is what you are going to get, right? This is what you are going to get. So this is going to cancel and you are going to get pi plus pi alpha by 2. So pi common 1 plus alpha by 2. Okay, this is what you are going to get. This is what you are going to get. So if I consider that the equilibrium pressure is this much, so if the equilibrium pressure is this much, or if we can take, there was initially 1 mole also we can take here. Okay, we'll take 1 mole is there, suppose. Okay, so if 1 is there here, we'll consider 1 here. Okay, suppose anything you are taking of that sort. Now here P, we get here what? We get equilibrium pressure as P. Now if we want to find out the partial pressures, the partial pressures will be PA, this will be PB, and this will be PC, and this is going to be PC. Now we know that partial pressure, this will be equal to equilibrium total pressure into XA. Yes, into XA. Yes, XA is nothing but the mole fraction. Yes, XA is nothing but the mole fraction. So if I want the total here, this will be 1 minus alpha plus alpha by 2. So this is nothing but 1 plus alpha by 2. This is nothing but 1 plus, total is, so total is 1 plus alpha by 2. So if I want here, this will be PA will be equal to P into XA. XA is, what is the pressure here, children? 1 minus alpha. What is the total pressure? 1 plus alpha by 2. Okay, this will be this much. Yes or no? Yes. So now we'll erase all of these. Now again, if you want for PB, P will be how much, children? This is alpha. Alpha is here and total is 1 plus alpha by 2 into the equilibrium pressure, which is P we have taken. Okay, you don't have to write the entire thing because P is going to get cancelled anyhow in the end. PC will be what, children? It will be alpha by 2 divided by 1 plus alpha by 2. This is going to be again P. Yes, okay. So you can take anything, you can consider initially it was Pi, you can consider, or you can consider 1. So as per your convenience, you can write whatever it is. Okay, so if you take 1, it becomes easier. So these are going to be the things here. Now we got in terms of P and alpha, you can substitute the values here, right, in terms of PB, PC, PA, and then you are going to get the answer easily. Okay, so that won't be an issue. So if you solve this, you have to solve it by yourself. So option B is going to be your answer. So you have to solve this on your own. You just have to take the values and put it there. So the most maximum work I have been done. Okay. Moving on to the next question, children. Again, a concept based question, a very small concept. Pause your screen and try, everyone. Okay, children. So let us solve this question. So before solving this, you should know that what is the relationship between Kc and Kp. So here we are going to talk about the relationship between Kc and Kp. So Kp is equal to Kc into RT to the power delta Ng. Okay, that is the difference in the number of moles. Okay, this is number of moles of gaseous product minus number of moles of gaseous reactant. Yes, okay. So if we see above, this one is in solid state, so we are not going to consider this. This one is in solid state, so we are not going to consider this. So if we consider in the product side, we are having 1 mole here. So if we consider the product, we have 1. If you consider the reactant, we have only 1 here, that is 3/2. So if we want to get delta Ng, that is going to be what, children? 1 minus 3/2. So that is going to be minus 1/2. So if I substitute the values here, so Kp will be equal to Kc into RT to the power minus 1/2. This is going to be the answer. But what are we asked? What are we asked? We are asked about Kc. We are asked about Kc. Yes. So if I take Kc, this implies Kc will be equal to, I have to take this to this side. So Kp by RT to the power minus 1/2. But if I take this above, the powers will become reversed, right? So this implies Kc will be equal to Kp into RT to the power 1/2. Okay, so this is going to be your answer. And that is in which option, children? That is in your option number D. So option number D is going to be your correct answer. Yes, so this was one takeaway concept from here, that the relationship between Kc and Kp we have discussed. Okay. Okay. Let us move on to the next question and see what concept awaits for us. Okay. Next question on your screen, everyone. Try this. Okay, children, let's see what's given in the question. It's given that the value of Kc is 64 at 800 Kelvin. So a reaction is given to us. Let us write down that reaction. And for this reaction, Kc will be what, children? Kc is going to be okay. So this is going to be your Kc. Yeah. Now this is given to us as 64. The value of Kc for some reaction is given. So is it the same reaction or the reaction has been reversed? We are seeing that the reaction has been reversed. So if we see here, the reaction, it is NH3. So it has been reversed, right? So when this it get reversed, so we have to take it in the denominator, right? So the equilibrium constant for this reaction is going to be 1 by 64. Yes. Also, is it just reversed? No. One more thing has also been done. And what has been done, children? See, wherever there is 1, you can consider that place. So it is 1 here. So this is half N2 here. So can I say it has multiplied by half? Or we can say it divided by 2. Yes. So if you multiply here half and here half, you're going to get the same thing. So when you multiply something, that goes on to the power. That goes on to the power. So this is the value. We have to take half to the power. Yes. And I hope you all know that when something is taken to the power, that is, if it is 1 by n, that means it is square root to the power n. So here it is 64, just like this. So it is going to be 1 by 8. Yes, square root of 64. It is going to be 1 by 8. And 1 by 8 is in which option, children? It is in second option. Yeah. No, this is not the answer, children. 1 by 64 is not the answer. Answer is 1 by 8. 1 by 8 is going to be your answer. Yes. Okay. Moving on to the next question. Okay. This is the easy one. Looks difficult, but very easy. Just try, everyone. Until then, let me see if you all have any doubts to ask. Okay, children. So let us see what is given here. For the equilibrium, A is to B. This is given to us here. The variation of forward and reverse reaction with time. So how are the forward and backward reaction? We know that at equilibrium, whenever there is equilibrium, yes, the rate of forward reaction is always equal to the rate of backward reaction. Yes, this is the concept of equilibrium. Yes, and also we know that K is equal to, let us see the diagram. So are these both equal? A and B equal? No. Is this case equal? No. Is this case equal? Yes, they have a common point here. Now, is this case equal? No. So we get only one answer, that is option C. So this is going to be your answer. Yeah. Why? Because here your RF and RB, they have a common point here, and that is equal. Let us go to the next question. Okay, next question on your screen, children. Try it, everyone. Okay, children. So let us see. It is given if the equilibrium constant is given. For this reaction, it's this much. For the other reaction, we have, it is this, right? Now we are being asked the equilibrium constant for A to P. How are we going to get A to P? Let us see. What can we do to this both that we get A to P? Can I say if we add both the reactions? Yes. So adding equation 1 and 2. Can I say that if we add equation 1 and 2, we are going to get, adding means you have to add this part only. So if I add this both part, yes. So now you can see this is on right hand side, this is on left hand side. So this both are going to get cancelled. When these both get cancelled, so what is remaining? You're having only this much. Yes, you're having only this much. Now, if I want the equilibrium constant Kc, it will be concentration of P by concentration of A. This is what I want, right? This is what I want. So how can we get this from 1 and 2? So if I see, for this, it is K1, it is concentration of B, C by A. For K2, if we see, it is concentration of P, B and C. So what can we do to get Kc? How are we going to get Kc? We need P above and only A below. So can I say we need only P above and A below? So can I say if we multiply this two equation, I can see that if I multiply these both equations, I'm going to get if I get this, can I cancel this? I'll cancel this with this. So am I going to get P by A? Yes. So I can see that. So if we multiply, so what is the, how are you going to get this? This is going to be K1 into K2. And that is in which option, children? It's an option number B. Yes. So option number B is going to be your correct answer. Yes, children. Okay. I hope you all understood this question. Yes. We'll move on to the next question. Next question on your screen, and take a minute and try this, everyone. Okay, so let us read the question. In the figure shown below, you have reactant A and it is represented by square. And it's in equilibrium with product B. So that is by circle. So I can say that A is in equilibrium with B, or I can say that your square is in equilibrium with circle. If I want the equilibrium constant K, what I have to do, I have to take the concentration of circle by concentration of square. Concentration here basically means the number, right? So we are talking about numbers here. Yes, children, we'll talk about numbers here. So talking about numbers here, let us count how many are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 here. Counting the number of squares, children. So how many do we have? 1, 2, 3, 4, 5, 6. So this is 6. Yes. So this is nearly how many times? This is nearly 2 times. Nearly how many times? This is nearly 2 times. And 2 times is in option number 1. So your answer is going to be 2. So it might seem difficult, but look what easy question it is. Yes or no, children? So this was a very, very easy question. Yes. So do not get confused if you get this kind of circles and squares. So you have to take the concentration. And here concentration means nothing but numbers. The numbers is the concentration. Concentration is the amount of substance of something. Amount of substance, how are you going to calculate the amount of squares or circles? Basically, you are going to see the numbers here. Yes. So those who would have understood this, that the concentration is equal to number, they would have been easily able to solve this question. Okay. Moving on to the next question. Okay. See everyone here. Take a minute and solve this. Okay, sure. So what is the question? In which of the following equilibria the value of Kc will be equal to Kp? So we want that Kc is equal to Kp. So again here, when we talk about this, we are talking about the relationship between Kc and Kp. We are talking about the relationship between Kc and Kp. We know that Kc or Kp is equal to Kc into RT to the power delta Ng. Now, if I want that Kp is equal to Kc, case 1. How can I get Kp is equal to Kc if this value becomes 1? If RT to the power delta Ng is equal to 1, this implies the Kp will be equal to Kc. Yes. And how are you going to get this as 1? If you get delta Ng equals to 0, this value should be 0. Delta Ng is 0 means number of moles of product minus number of gaseous molecule is to be 0. That means we are talking that the same number of gaseous product, moles of gaseous products and gases, that is same number of gaseous products and reactants. Yes, so wherever that will be the case, that is going to be the answer. So let us discuss the first case. So here it is 1, here it is 1, it is 1. So if I look at the delta Ng here, what is going to be my delta Ng, children? This will be 2 minus 1, which is not equal to 0. So this is not the case. Yes. Moving on to the next. This is 2 here. This is 1 here. So this total is 3. This is 2. So this will be 2 minus 3, which is minus 1. So that is also not equal to 0. Yes. So this is also not going to be the case. So this is 1 here. This is 1 here. This is 2 here. So this is a sum of 2. So your delta Ng will be equals to 2 minus 2, which is equal to 0. So this is going to be our case. We know this. But for our safety, we are going to check the next option as well. Yes. So this is 1 here. This is 3 here. So if we add this, we are going to get 4 here. This is 2 here. So talking about delta Ng, we are going to get 2 minus 4, which is not equals to 0. So this is also not going to be our case. Only one option is correct. That is your option number 3, right? So which one, children? Option number 3 is going to be the correct answer. So what did you understand from here, children? In order to be the Kc equals to Kp, your delta Ng should be equal to 0. Yes? Okay, so this is the takeaway concept from here. Let us move on to the next question. There is something here. We'll see what is given here. It is a definite value for all chemical reaction. It is about equilibrium constant. Both Kp and Kc are our equilibrium constant. We all know that. When do we use Kp? When the concentration terms are given in partial pressure. That is for most gaseous reactions. Instead of using Kc, we use Kp. When we use Kc, when they are expressed in molarities, then we use Kc. And if you want to see the relationship, this is given as a relationship. Okay. And this delta N is a change in moles of gases, not the entire number of moles. If you take the entire number of moles, you are going to get a different answer. You're going to get a different answer. So if we are talking about delta N here, delta N is a change in the number of moles of gases in the reaction. Okay. Let us move on to the next question, children. Yes. So this question is from, I'll give you a hint. This is from Le Chatelier's principle. Yes. So try this, everyone. Pause for a moment and try this question. Okay, I just discussed what is delta N. Which number question are you saying the option 2? Okay, so delta N, children, is the number of moles of gaseous product minus number of moles of gaseous reactant. Yes, that is the case here. For example, if we are having H2 plus I2 give rise to 2HI. So this is the product, this is the reactant. They are all in gaseous state. So delta N will be, if you calculate the number of moles of product, that is only 2 here. Minus, if you see for reactant, this is 1, this is 1. So this is 1 plus 1, 2. So 2 minus 2 is 0. So that is your delta N. Yes? Is it clear? Okay. So let's see what is given in this. What is given here? Let us see. It is given here that there is a gas phase reaction. And this is an exothermic reaction. It is telling that the decomposition can be increased by. Decomposition means we have to move towards the product. We are moving towards the product. Now, if you consider the number of moles here, this is 2 moles here. And this is 1 mole here. So can I say, children, we are moving towards lesser number of moles? Yes, we are moving towards lesser number of moles. So what happens? When are we going to move towards lesser number of moles? It is an exothermic reaction. What reaction, children? Exothermic reaction. So in case of exothermic reaction, if you increase the pressure, is it going to do? No. So what is going to do? If you add an inert gas, so what happens when you add an inert gas at constant pressure? So when you add an inert gas at constant pressure, the volume is going to increase. So you had this gas, then you are adding an inert gas. You are adding an inert gas. Okay. So just a minute, children. So this is asking us about the decomposition of N2O4. We are talking about the decomposition of N2O4. Yeah. So we want to decompose N2O4. Yes. So if we want to decompose, if we are looking at the forward reaction, it is being asked us about what? It is being asked us about moving towards N2O4. We are asking about decomposition of N2O4. So if we introduce an inert gas, then what is going to happen, children? Your volume is going to increase. Volume increases at constant pressure. Yes. So when your volume is increasing at constant pressure, then what it is going to happen, children? You are going to move towards lesser number of molecules. You are going to move towards lesser number of molecules. That is, the decomposition will be increased. Yes. So if you add an catalyst, your decomposition is going to increase. Yes or no, children? So adding an inert gas is going to be your correct answer. So do mention me in the comment section why other options are not possible here. Yeah, why other options are not possible. Give me what happens when you increase pressure, what happens when you lower the temperature. So we'll keep a class about your Lee-Chatelius principle and those concepts in the next class, right? So let us look at the next question. Probably this is your last question. Yes. Okay. So let us see what is given here. Just read it for a moment, then I'll solve this. Okay. So what is given here? It is given that two solids dissociate as follows. Now it is asking the total pressure when both the solids dissociate simultaneously, then what is going to happen? Yes. So we know that if we look at the equilibrium constant, the first one, it is going to be partial pressure of B into partial pressure of C. We are not going to consider this because it is in gaseous phase. So this is P1 and this is going to be P1 plus P2. Yes. So can I say that P1 into P1 plus P2 is equal to X? This is given to us. Now talking about C, this is going to be P1 plus P2. This is only P2. KB will be what, children? PC into PE. Yes, because again this is your solid. Now can anyone tell me why I took this as P1, this is as P1 plus P2? Do let me know. Why have I taken it that way? Yes. Okay. Now if I see here, this is going to be PC is P1 plus P2 into P2 is equal to Y. This is given to us. Now what it is telling to us, if I want X plus Y, if I'll add this both equation, adding equation 1 and 2, because they are dissociating simultaneously, right? So if I adding 1 and 2, what am I going to get? P1 P1 plus P2 plus P2, P1 plus P2 is equal to x plus y. If I take P1 plus P2 common, we'll have P1 plus P2 is equal to x plus y. Yes. So if we solve this, we'll get P1 plus P2 whole square is equals to x plus y, which implies that P1 plus P2 is equal to root over of x plus y is equal to root over of x plus y. Right? Now, but is this the end of question? No. What is being asked to us? It is asked to us when both the solids, the total pressure is asked to us. What is asked, children? Total pressure. So total pressure will be PA, not PA, because PA is solid. So all the gaseous. So PB, PC, PE. So the total pressure will be PB plus PC plus PE. And what is your PB, children? PB we have taken as P1, PC we have taken as P1 plus P2, and PE we have taken as P2. Now if I see this, I'm getting P1 plus P2 plus P1 plus P2. I'm getting 2 into P1 plus P2. And what is the value of P1 plus P2 I got? I got it as root over of x plus y. I got it as root over of x plus y. So this is going to be 2 into root over of x plus y. Yes, this is going to be 2 into root over of x plus y. Yeah, so that is your correct answer. And it is in which option, children? It is in option number 4, and option number 4 is your correct answer. Okay, children? Okay. So in the next class, what are we going to do? We are going to discuss some more concepts based on chemical equilibrium. Yes, we'll discuss Lee-Chatelier's principal question. We are also going to see some questions on ionic equilibrium in the further lectures. Yes, so this is what we are going to discuss in the further lectures. So until that much, you all have to revise what is being taught till here. Okay, you have to revise what is being taught till here, and the rest we are going to continue in the next class. Okay, children. Thank you, children, and bye-bye.